All right, AP students, welcome to your Unit 3 walkthrough. We'll do one or two conceptual, and then we'll head straight into the AP. This should be a shorter walkthrough problem video. And let's go ahead and begin. So Unit 3 is all about the interaction between particles. So we're taking a step back from bonding, and we're looking at, well, how do particles now interact in a large sample? Because at the macroscopic level, at our everyday level, we're working with vast amounts of particles that together make up a sample that we can actually interact with at our level: sense, see, taste, touch, smell, so forth, right? So we were introduced to three types of intermolecular forces. And this first question asks you to identify the dominant IMF present in each of these different molecules. So the three types of IMFs were called London dispersion forces, dipole-dipole, and hydrogen bonding, but not real bonding, just very strong, okay? And all of these get increasingly more rare and increasingly more strong. So everybody has London dispersion forces present because it applies to all molecules, and particularly it's the only force that non-polar molecules can engage with. It's based off of temporary dipole formation through the temporary shifts and movement of electrons within a molecule that will create a temporary shift or movement of electrons in another molecule. So when we look at this question, what we see is that I2, your diatomic, okay, compound, your diatomic molecule, only has one IMF it can engage with because it is non-polar, being bonded to an atom just as electronegative of itself. And so what we would see is that the dominant IMF for this compound is going to be, London dispersion forces. I'm going to represent with LDF, okay? Now, we move on to the next one, HCl. We know that HCl is one obviously going to have London dispersion forces, but the question is, what is going to be the dominant one? What's going to be the IMF that's kind of unique to it? Well, we know HCl is an ionic compound, despite it being two nonmetals. We see hydrogen, which is on the right side of the table, super low electronegativity, pairing up with the exact opposite, chlorine, which is a halogen on the completely left side versus right side of the table, the opposite side of the table. And as a result, we already know from our work in Unit 2 that HCl is an example of an ionic compound, which means there is a permanent, okay, polarity, not just dipole, but like a permanent polarity, the most extreme version of a dipole you can get. And so we know that this is going to engage in not only LDFs, but also dipole-dipole. Okay. And so that is the dominant IMF present. And then we look at NH3. Well, we know that NH3, of course, is going to have London dispersion forces. But based off of the Lewis structure, we also know NH3 has this lone pair around the central nitrogen. So despite having equivalent terminal atoms, what we see is that we have this high zone of electronegativity due to the very negative, just fat squishy squish of an alone pair electron on top of the central nitrogen. So what we're going to see, it's going to have dipole-dipole. But it's not only going to have dipole-dipole, we also see that this is a compound made up of NH bonds. And NH bonds are part of the stipulations for hydrogen bonding, that hydrogen is attached to a nitrogen, or hydrogen is attached to an oxygen, or hydrogen is attached to a fluorine, directly attached in the molecule. So we see that actually the dominant IMF present, the most unique IMF present in this molecule, is going to be H bonding, or hydrogen quote unquote bonding. It's not real bonding, it's just so strong, it's like a bond. All right. So that's kind of like your really brief conceptual overview on IMFs. I have one more I want to walk through, and that is down here. where we talk about particulate diagrams. Particulate diagrams are super, super important in the AP exam. It's just a common MCQ, FRQ for you to read, to create. As we progress, you'll learn the ratios by which we draw in molecules are really important for correctly and effectively using particulate diagrams. But for right now, we're just starting off easy with some simple illustrations and interpreting them. So right here for question 9, we have which two particles represent the mixture of diatomic elements. So a diatomic element is, of course, your Brinkelhoff, right, elements. And we know that they are always paired together. So it's Br2, I2, N2, chlorine 2, H2, O2, and F2. When you think they're alone at a neutral state, they're always actually with one of them, another version of themselves. And so, or another atom of themselves. And so what we look for here is what two particles show the same two atoms being paired together, right? So remember, color here is going to represent element identity. Sounds silly that we're going over this. When you're going to be asked to draw these, you're going to want to keep in mind all the little nuances and meanings that you give that particulate diagram intentionally or unintentionally, okay? And the goal is to always be intentional about it. So what you see here is that we look at A and we have a series of two black molecules and one white molecule. And then we see that they're paired with similar atoms. So we would say that A is one of the diagrams. We look at B and we see, oh, again, 3 sets of 2 black atoms, but we have a black and a white, which tells me this is actually a compound made up of 2 different, okay, elements. So we're not going to do that one. We look at C and we see 3 white paired ones and 1 black paired one. And we would say it would be C as well. And then of course, D is a bunch of compounds, 3 compounds, okay, with 1 diatomic. So we definitely know D is not an option. So it becomes A and C. Okay, easy peasy, lemon squeezy. Let's go ahead and move on to the AP problem. What you're going to start noticing is as we progress in AP problems tend to actually sometimes aren't even directly connected to the unit and they just have like one sub question that is related to this unit. But I couldn't release all that until we got to this unit. But you're going to start noticing that AP questions become multi-united questions. So for question 1, this is a short FRQ worth about 9 minutes according to the AP, and it's worth 4 points. So use the principles of atomic structure and or chemical bonding to explain each of the following in each part, okay? Your answers must include references to both substances. So they tell you right away that they want you to explain both. All right. So what we have here is the atomic radius of lithium is larger than that of beryllium. So this right here is actually a unit 1 question, right? Periodic trends. So what we need to say is that 1, lithium and beryllium in the periodic table are side by side in row 2. Lithium has a proton number or an atomic number of 3. Beryllium has atomic number of 4. So what we need to identify is that if we're looking at radius, there are 2 things that can affect radius. And all of it really stems down to Coulombic attraction. The first is charge, and particularly proton count. And the next is distance, and particularly electron count. When we look at this, we see that they're in the same row. So we automatically can identify that the distance is not really the issue that is going to separate them or their explanation for why the radius of lithium is larger than beryllium. So then we look at proton count and we say to ourselves, oh, well, lithium has less protons than beryllium, resulting in a weaker, all right, Coulombic attraction, all right, experienced by the electrons. Okay. And that would result in the atomic radius being larger, okay, given that the ratio between protons, all right, or actually given that, let me rephrase that. Let me say it a different way. Larger, given that no energy level change has also occurred between these two elements or atoms. All right. So my answer addresses both the fact that charge is the only thing that's changing and the fact that distance didn't. And I explicitly state, okay, the role that each plays in determining why lithium has a larger atomic radius. All right. You could also, instead of saying Coulombic attraction, you could also say effective nuclear charge. That would have been also a great way, because remember, Coulombic attraction is actually kind of like the vague understanding, but in chemistry, we can specify it as effective nuclear charge, like a weaker effective nuclear charge, right? That's another way you could put it. So B, the second ionization energy of K is greater than the second ionization energy of calcium. Okay, so explain this. So K and calcium are similar to lithium and beryllium in terms of they're both in row 4, but calcium has a 19 proton count, and potassium has a 19 proton count, calcium has a 20 proton count, and this is in column 1, and this is in column 2 on the periodic table. So what we see for this one is when we look at ionization energy, or the energy required to remove an electron, okay, we see that calcium is going to want to lose 2 electrons to become like the noble gas argon behind it. But potassium is going to want to lose 1 electron to become like the noble gas behind it, which is also argon. So when we look at the ionization energies, we notice that let's start with potassium. Potassium, okay, only wants to lose 1 electron, or is favorable, right, to the process of losing 1 electron, only wants to reach stability, or you could even say an octet, right? And thus has, okay, a high second ionization energy boom, boom, boom. And this has a high second ionization energy due to the resulting breaking of the octet, okay, if the second electron were removed. All right. On the other hand, right? On the other hand, right, calcium is totally, all right, totally calcium favors, okay, or is favorable towards is favorable or is, yeah, favorable towards removal of second electron. We also need to recognize that every time we move an electron, right, you get a greater effective nuclear charge, a greater ratio between the proton count and the electron count. So for both, though, they would demonstrate a slight jump in ionization energy from first to second, simply because you also have a greater effective nuclear charge being experienced. So we could also say, generally, the second ionization energy is greater due to greater effective nuclear charge being experienced. All right, effective nuclear charge experienced. So that's one way you could explain it. Let's go on to the third one, C. The carbon to carbon bond energy in C2H4 is greater than that in C2H6. So you might want to draw out the Lewis structures, and what you would find is C2H4 is ethene, which is a double bonded, whereas C2H6 is what we actually call ethane, and it is all single bonds. So what we see here is C2H4 has a double bond with a bond order of 2. And remember, double bonds tend to be shorter and stronger, whereas C2H6 or ethane has a bond order of 1 across the entire molecule. So what we need to do to explain is, why do we see the carbon to carbon bond energy in C2H4 be greater than that in C2H6? Well, C2H4 contains a double bond, okay, between the C and C, whereas C2H6 only contains a single bond. Okay, double bonds, okay, are stronger and have shorter bond length, resulting in a higher bond energy than single bonds. Okay. So that would be the result there. And how about this one? Here is now the unit 3 specific portion. The boiling point of Ci2, or no, sorry, Cl2, chlorine 2, is lower than the boiling point of bromine 2. So here we're comparing the two diatomics. Now, chlorine and bromine are both halogens. And what we see is that chlorine is a row 3 or energy level 3 element, and bromine is an energy level or row 4 element. So what we would see then is that as we go down, the radius, okay, is increasing. All right, so the other thing that we recognize too is, if we're talking about boiling point, we also know that boiling point is directly connected to the IMFs present, okay? So what we see here is, right now we notice that chlorine and bromine, okay, or diatomic chlorine and bromine, both are nonpolar and experience LDFs, or London dispersion forces. You would probably write that fully out, okay? But for my sake, just because I don't have much space, I'm just going to write LDF for London dispersion forces. So as a result, we know that the IMFs aren't the reason. Well, I'll put it this way. London dispersion forces, okay, are not explicitly the variance that's causing the boiling point to be greater or lower than their respective other diatomic. But what we do know is bromine, okay, particularly diatomic bromine, is in a greater energy level and has more polarizable, because remember, electrons can move around and they create temporary dipoles. They have more polarizable electrons available. Okay. And that matters because the only way London dispersion forces actually change within a nonpolar molecule is depending on the amount of electrons you have available to create a greater mass shift or a weaker shift. So what we see is that bromine, diatomic bromine, is in a greater energy level and has more polarizable electrons available, resulting in stronger LDFs experienced by bromine 2. So greater IMFs are like directly related or result in a higher boiling point. Right? As it takes more energy to break apart those interactions. So that's kind of your overview right there. It is a lot of writing, a lot of the AP questions, as you're starting to notice, are very conceptual explanation based. And then you, of course, have your math based, right? But your ability to explain is a huge skill in the AP exam. All right, guys, really good work. That's the end of today on AP questions because I don't think I selected any more. Nope. And good luck. I'll see you tomorrow. Bye.